In the last video, we met the Heaviside function, also called the unit step function, and we talked about how this function gave us a way to delay the start of an external forcing. That was one situation, and that's what we'll look at today. But we also briefly looked at the fact that you could use the Heaviside function to turn off a signal or to turn a signal on and then off. Today, we'll just focus on the basic application, which is to turn on a signal after some time has gone by. We will have two examples, a basic first order example, and then we'll look at a second order example. Our first example is a pretty basic first order equation. We have dy dt equals h of t minus 2. So this right-hand side is 0 for time values less than 2. And then right when, say, 2 seconds have gone by, we flip that on and it becomes just plain old 1. So there's not too much going on this right-hand side. The next example will be a little bit more complicated. We also have an initial condition, of course, that when time is 0, the position of this solution to this differential equation is 1. Now, this is not a very big equation, and you can actually reason out what the solution would be just by visualizing this first derivative. In fact, let's do that. Kind of a neat exercise. dy dt is 0 until 2 seconds have gone by. So that must mean that our position function y is constant. What is that constant value? It comes from the initial condition. So y of 0 is 1 means that from the start until t equals 2, we are at the constant value of 1. Then after that, dy dt is 1. That says that from this position afterwards, our function has a constant slope of 1. So that's going to look like this. And there's a graph of the solution. Let's write down an explicit form so that when we solve this with the Laplace transform, we'll be able to verify that we did it correctly. Okay, so what function is this? It's a piecewise defined function. It's this constant value 1 if t is less than 2. We could go ahead and fill it in as 1 right at t equals 2, but I'm just going to leave that spot empty. And then what is it at t equals 2 or beyond? Well, let's see. If this were the origin, we would be looking at y is t plus 1. But we have to shift it by 2. So instead of t plus 1, I need to take t and shift it by 2 to the right. So I imagined first that this was the y-axis, and then I would be looking at the function y equals t plus 1, y-intercept 1. But it's not because we translated by 2 to the right. So that's how I was able to write this down. However, we can actually take this piecewise expression now and put this into one line using the Heaviside function. Notice we have 1 here and 1 here. So this value of 1, we treat that as the same number 1. It always appears. So I'll say, okay, we've got 1. And then we are going to add to that t minus 2 starting at 2. So that's going to be where the Heaviside function makes an appearance. Okay, so to the left of 2, this is 0, and all we have is 1. That's what we see here in this first line. But then to the right of 2, this is 1, and so we get the t minus 2 plus 1 that we have here. All right, this is the solution to this differential equation. Let's see if we can get to it now with the Laplace transform. All right, let's take the Laplace transform of both sides. For the left-hand side, because that's the Laplace transform of a derivative, I will go ahead and apply the relevant identity. It's going to be s times the Laplace transform of our solution y minus y at 0, which we know to be 1. On the right-hand side, we need to take the Laplace transform of the Heaviside function t minus 2, h of t minus 2. Okay, y is unknown, so we have s times the Laplace transform of y. In the last video, we found the Laplace transform of h of t minus 2. We did it in terms of h of t minus a. It was e to the negative 2s times 1 over s. Okay. And then we need to add to this y of 0, which is 1. Okay, so that's our right-hand side. Divide by s, and we can isolate the Laplace transform of y. So the Laplace transform of y is going to be e to the negative 2s 1 over s squared. Do you recognize what that's the Laplace transform of? Plus just plain old 1 over s. No further work is needed in this equation. There's no partial fractions or anything like that. We're ready to back out of this what y must be. So you might want to start here. So what is the inverse of this? So what function do you take the Laplace transform of to get 1 over s? Here, this looks like the Laplace transform of a delayed signal. We worked through the general principle in the previous video. So assuming you've seen that, can you map this expression into a Heaviside function times a shifted forcing function? All right, you might have also needed to check a Laplace transform chart to remember what the inverse of 1 over s squared is. It's just t. So let me write e to the negative 2s times the Laplace transform of t plus 1 over s is the Laplace transform of the constant function 1. Okay, this product here, this e to the negative 2s exponential times a known Laplace transform is exactly the result of taking the Laplace transform of a delayed signal. So the inverse Laplace transform of this is going to be t shifted 2 units to the right and turned on when t equals 2. All that to say that our solution y of t to this differential equation is going to be, well, again, this looks like t, but we need to shift it 2 units to the right and turn it on at that moment. So h of t minus 2, the Heaviside function times t minus 2, and then plus 1. And that is exactly what we got through that visual analysis. All right, this was a warm-up for our next example. We're going to do a second-order differential equation next. All right, in this example, we would like to solve the second-order equation y double prime plus 3y prime plus 2y equals h of t minus pi times sine of 2 times t minus pi. So this right-hand side indicates that when t equals pi, we're going to turn on a sinusoidal forcing function that looks like sine of 2t. So we're taking sine of 2t and shifting it by pi units. Fun fact, sine of 2t minus pi is the same thing as sine of 2t, but that's just a little quirk about this example. It's set up to indicate that we have shifted the origin for the forcing function, and then we're turning it on at that moment too. To solve this, we're just going to take the Laplace transform. We'll bring in these initial conditions as we do. I will go ahead and use linearity on the left-hand side to say that this is the Laplace transform of y double prime plus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y equals, and then on the right-hand side, we're going to take the Laplace transform of this kind of delayed signal, h of t minus pi times sine of 2 times t minus pi. There we go. Like that. Okay, for the left-hand side, we'll use our first and second derivative identities. So the first term is going to be s squared times the Laplace transform of y minus s times the initial condition y of 0 minus y prime at 0. And then plus 3 times the Laplace transform of y prime is going to be plus 3s times the Laplace transform of y minus y at 0 plus 2 times the Laplace transform of y. Okay, pick up like the whole row. On the right, we're taking the Laplace transform of a huge expression, but actually it's really not that bad. It's going to have that form. It's e to the negative pi s times the Laplace transform of the unshifted forcing function. So removing the shift by pi means that I now want to take the Laplace transform of just plain old 2t. So that's going to be 2 divided by s squared plus 2 squared, so s squared plus 4. Okay, so it's really not that bad, right? So from a huge expression to something pretty simple looking. Okay, on the left-hand side, let's gather our Laplace transforms of y And for convenience, I went ahead and made y of 0, 0, just to reduce the computational complexity here. So that's 0, this is 0, and y prime at 0 is 1. So that's going to look nice. Gathering like terms on the left, as expected, our left-hand side is going to look like the characteristic equation of the left-hand side. So s squared plus 3s plus 2 times the Laplace transform of y. And I will go ahead and bring this constant over, and I think that's the only thing left on the left-hand side. So we'll have e to the negative pi s times 2 over s squared plus 4 plus 1. Our quadratic on the left-hand side factors. So we have s plus 2, s plus 1. So then on the next line, what I'm going to do is isolate the Laplace transform of the function y that we're looking for. And on the right, we are going to divide both of these expressions by this product, s plus 2 times s plus 1. But as I write that, what I'm going to write instead of 1 divided by this whole expression, I'm going to go ahead and set it up for the partial fraction decomposition. So leaving the Laplace transform of y on the left. For this first term, I will write e to the negative pi s, and then we're going to have 2 divided by s squared plus 4 times s plus 2 times s plus 1. Setting that up for partial fractions, it's going to look like as plus b divided by s squared plus 4 plus a constant, I'll call it c, divided by s plus 2 plus a constant d divided by s plus 1. And then plus 1 divided by that product. Again, setting this up for partial fraction decomposition, let's write e, that's where I left off, e divided by s plus 2 plus f divided by s plus 1. Okay, so what I do myself is I just use a tool. There are online widgets that do this for you. I like to use Wolfram to do this partial fraction decomposition. If you would like to work this out by hand, you're welcome to. So I will step aside for a few minutes. And if you would like to see if you can work out the constants A, B, C, D, E, and F, that's fine. But the goal of this problem is really to just work through how the Laplace transform allows for us to solve for this unusual second order equation, the type that we haven't worked with before. Partial fractions is not really the objective here. So in a moment, I will come back and I will just replace these letters with the correct values. Before I step away, let me mention here that because this is an irreducible quadratic, make sure when you set up the partial fraction decomposition, you do it correctly. It's irreducible quadratic, so the top has to be as plus b, not just a constant. All right, so I'll be back in a second to reveal what the partial fraction decomposition should be. All right, whether you worked it out by hand or with some kind of tool, the constants you hopefully got were negative 3 over 20, negative a tenth, negative a quarter, 2/5, negative 1, and 1. I've got a really full board here, but I think I can finish. If not, we might need to erase and start with a fresh board. I now want to find the function y, which has this Laplace transform. Well, Laplace transform, you can do it piece by piece through linearity. So this is going to invert to negative e to the negative 2t. That's great. This is e to the negative t. That's also great. What might feel a little uncertain at the moment is this leading expression, because this is the new type of information that we're looking at due to this delayed forcing. So in other words, this is going to correspond to the homogeneous solution and this to the particular solution for this differential equation. Let me write this expression one more time. And as I do so, I'm going to start saying the Laplace transforms that I recognize immediately. I do recognize these immediately, but I'll leave that for another line. Let's say e to the negative pi s times, here I'm going to break this up into negative 3 over 20 times s over s squared plus 4. Now that looks like a cosine. Minus 1 over 10 times 1 over s squared plus 4. And pause here. This looks like sine, but because this expression here is like omega squared, and we would like to have omega in the numerator, I'm going to take that 1 and turn it into a 2 and then make this 1/10, 1/20th. Okay, now these are ready to go. Here, this looks like -1/4 times the Laplace transform of e to the -2t. Oh yeah, I'm definitely going to need more room. Okay, let me just finish what I'm doing and then I'll step aside, let you copy it down, and then we'll start over with a clean board wherever we left off. So, okay, this expression here looks like -1/4 times the Laplace transform of e to the -2t. Similarly, this one looks like 2/5 times the Laplace transform of e to the -t. Okay, that ends the particular solution component. And then we have already said that this looks like negative Laplace transform of e to the -2t plus the Laplace transform of e to the t. Okay, let me give you a moment to copy all this down and think about it. Then I will erase everything when I come back. Let me say one more thing before I step away, and that is that we have here a Laplace transform of a known function with this scaling exponential in front, e to the -pi(s). What that does, kind of like what we saw with the first example, is it's going to say, and here I'm just trying to highlight this pairing, that we need to just take e to the -2t, shift t by pi, and multiply by the Heaviside function. So we're really just about done. Each of these components inside the square brackets here is going to invert to its regular inverse. Like this is going to be cosine, a sine. We already have the exponentials here identified. But then we just have to shift t, the time variable, and multiply all of them by h of t minus pi, which we'll leave out front. If you're feeling ambitious, go ahead and do that. So see if you can write down the final answer, and then I'm going to erase everything just to make it really clear at the end what we're looking at. Let's invert this Laplace transform. On the left, we are going to arrive at the solution for this differential equation. And then, as I was saying a minute ago, looking at these first 4 expressions inside the square brackets, each one is being scaled by this exponential out front. So each one of these is going to invert to a forcing function which has been shifted by pi units and which is turned on when t equals pi. That action of turning them all on, we can leave out front. So what I had is the exponential here. I'm now going to write the Heaviside function h of t minus pi. That hits all of them. So we'll leave that out front. Now what I'm going to do is invert each one. They just invert in the usual way, except whenever we write time variable t, we need to take that and shift it by pi because we've shifted the origin for these functions. So the first expression, -3/20, this would normally invert to cosine of 2t, because 4 here is 2 squared. So cosine of 2t is the normal inverse of this Laplace transform, but we need to shift that by pi. Similarly, the next expression will be -1/20 times sine of 2 times t minus pi. I think I'll drop down to the next line to invert the remaining 2 inside the square brackets. We'll have -1/4 e to the -2t normally, but we need to shift that by pi. Watch your parentheses in each case. Make sure you don't write -2t minus pi. It's not the same thing. And then lastly, plus 2/5 e to the -t, but shift that t by pi. Leave the negative out front. So the time variable is being shifted by pi. You have to be very careful with your parentheses here. That takes care of the particular solution. For the homogeneous part, we have minus e to the -2t plus e to the -t. All right, that wraps up this example. I know it looks like a really big computation. I mean, we basically filled this board twice, but hopefully we did it in a way which is systematic enough that you feel confident going forwards with these kinds of Heaviside functions where you have this shifted forcing function on the right-hand side. What I would like to do is leave you with an illustration of the solution to this differential equation. What you will notice is that between t equals 0 and t equals pi, the solution is going to look like decay. Well, actually, it might not start out looking like decay because our initial position is 0, but we have a velocity of 1. So it's going to initially increase, but you'll see that it looks ultimately like it's going to be a decay. But then when time equals pi, we are going to turn on all this other stuff. Now, what does this look like? These decay, but these don't. So we will have, after pi, some oscillation. You'll see oscillations because of the cosine and sine terms, and those will endure because they do not decay.